Hello, my name is Arman Kosami, and this is my quality control video report for WWC Industrial Chemicals, where I'll be determining whether an unknown copper sulfate solution meets the industrial specification of 0.5 to 0.7 moles whilst using gravimetric evaporation. To contextualize the investigation, I'll first outline the key theoretical concepts underpinning analytical chemistry. As presented, stoichiometry describes the numerical relationships between the reactants and products in a chemical equation and is grounded in the law of conservation of mass, which states matter cannot be created nor destroyed. To ensure this, we must balance the equations by both making sure the number of atoms on both sides are equal. Mole is a standard unit of measurement used to quantify particles in chemistry. 1 mole represents 6.022 times 10 to the power of 23 particles, which is known as Avogadro's constant, which can allow chemists to relate the microscopic scale of atoms to measurable quantities such as mass. The formula is depicted as N equals to M over mm, where N is the number of moles, M is the mass of a substance, and mm is the molar mass. Mole ratio relates the quantities of substances in a reaction using coefficients from a balanced equation. As represented, mole ratio can be expressed in this example. Concentration is in the quantity of solute per unit volume of solution, which is most commonly expressed as molarity in mole divided by liter. This can be categorized into two subcategories. Theoretical yield is the maximum possible product, assuming the limiting reactant is completely consumed with no losses. Actual yield, which is what is physically collected after an experiment. Percent yield is calculated as actual yield divided by theoretical yield, multiplied by 100 to get the success percentage. A key industrial example is the contact process, which is used to manufacture sulfuric acid, acting as in fertilizer production, batteries, and petroleum refining. The example of stoichiometric relationships is shown with the calculations. Therefore, the number allows plant engineers to assess efficiency and identify production losses in real time and highlight the importance of stoichiometry in industrial settings. Now for the aim and the hypothesis. The aim of our experiment was to determine whether an unknown concentration of copper sulfate solution meets the industrial requirements of 0.6 plus minus 0.10 moles per liter while using evaporation and evaluating the effectiveness of colorimetry as a replacement method. And our hypothesis was that the concentration would not fit into the range because of the unknown concentration of the solution. Please feel free to pause the video at any time. This is the risk assessment table which we used to conduct our safety throughout the experiment. This is the equipment list which was used to conduct the experiment. Serve the Bunsen burner and evaporate the copper sulfate solution until it reaches a light blue color and crystallized form as shown in the slide. As shown, the weights of the trial are from 1 to 5 are 1.12, 1.45, 1.17, 1.35, and 0.94 grams, with an average mass of 1.1 grams. The graph represents the overall trend of the evaporation process. As you can see, this is the calculation process used to define the average concentration of evaporated copper sulfate, and is shown that the concentration is below the required range of 0.5 to 0.7 moles per liter range. The aim of the experiment was to determine the concentration of copper sulfate using evaporation. The method works by heating the solution to evaporate the solvent, which leaves behind copper sulfate crystals. These crystals can be weighted and used to calculate the concentration. The method was valid because the mass of copper sulfate remaining after process was used to determine the concentration. To maintain validity of the experiment, some factors such as the solution volume, apparatus, and heating method were kept consistent throughout all 5 trials. In the investigation, the average concentration we obtained was 0.46 moles per liter, which lies below the industrial standard, indicating that the experiment was less accurate than expected. However, several experimental factors may have contributed to this. For example, splattering of the copper sulfate crystals during heating would have reduced the mass of solute measured. Additionally, incomplete transfer of the solution into the evaporating basin or measuring cylinder could have lowered the amount of copper sulfate present. Finally, measurement uncertainty from using our eyes to measure in the measuring cylinder compared to using a more calibrated device affected the accuracy and the final calculations of the experiment. The multiple trials in our investigation yielded a reliable average concentration to be calculated. However, variation between trials 2 and 5 suggests random errors occurred during the experiment due to a 0.2 moles per liter difference in results. Possible causes of the variation are differences in heating time, small measurement errors when we weighed the equipment, or an incomplete evaporation in some trials, which would have been affected with the final mass and consequently affected with the entire reliability of this experiment. To improve the accuracy and reliability of the experiment, we could have used a hot plate or water bath, which provided a more controlled heat below the boiling point and eliminating splatter, ensuring the full mass of copper sulfate is retained in the basin for weighing. Using desiccator would further reduce measurement uncertainty as well as using more calibrated equipment for measurement. Repeating the trials more would have weed out outliers in the experiment and possibly made the concentration reach industrial standards. The alternative technique is colorimetry. While gravimetric evaporation determines the concentration by evaporating the solvent and measuring the remaining mass using stoichiometric calculations, colorimetry measures the amount of light absorbed by the solution. In terms of industrial relevance, some important factors to consider are throughput and how colorimetry and evaporation need to meet this criteria. Throughput refers to the number of samples which can be analyzed within a certain period of time. While gravimetric evaporation has a lower initial equipment cost, colorimetry allows an industry to analyze the concentration faster due to a calibration curve, which determines the concentration using a solution with a known concentration as a reference, which is why it is recommended for WWC industrial chemicals to utilize colorimetry for a more practical and efficient production of their material. As shown in the table below, both methods offer high precision. However, colorimetry provides a near-instant digital readings compared to the slow heating and cooling cycle for evaporation, whereas the mass of copper sulfate during colorimetry is not susceptible to mass losses from splattering or incomplete evaporation. The experiment found copper sulfate solution had an average concentration of 0.46 moles per liter, which is below the acceptable range of 0.5 to 0.7 moles per liter, which supports the hypothesis and fulfilling the aim.